In this video, we'll see how to set up an integral with respect to y. So looking at the diagram, we have two curves. The first is written in the form x as a function f of y, and the second curve is written in the form x as a different function g of y. And we have that f of y is greater than or equal to g of y. What that means in terms of the diagram is that the curve given by f of y is to the right of the curve given by g of y. It's to the right because it's in the more positive x direction. We want to compute the area of the shaded region, but because the region is oriented slightly differently, in this case we're going to set up the integral with respect to y. So to do it, we subdivide the interval, so this time along the y-axis, into subintervals. And then again we choose an arbitrary interval in the middle somewhere. And we mark off a point, and again because it's on the y-axis, we'll label this point y, and then we draw the approximating rectangle for this interval. And so the idea is still similar to before, right? So we compute the area of this rectangle, and then we sum over the interval. So what is the length of this piece here? So because it's with respect to y, this length is going to be represented by dy. And then the length of this piece here is the distance between the two functions. So this function is f of y, this function is g of y. So the distance here is computed by, again, taking the difference. So we get f of y minus g of y. Okay, so now to compute the area. So the total area. So first, the area of the single rectangle is going to be height times width again. So one dimension is f of y minus g of y. And then the other dimension is dy. We multiply the two, so that's the area of the single rectangle. And now to get the total area, we integrate over the interval. Right, so we integrate from the lower endpoint to the upper endpoint. So from C to D. Now we're going to try to apply this method to an example. So let's scroll down. So the problem is to try to compute the area of the region bounded by the curves x equals y minus 2 squared over 3 and y equals 8 minus x. And so I've drawn and sketched the two curves. Right, so the first curve is the brown one here, and the second curve is the blue one here. So the problem is to compute the area of the region in between here. If you look at the region, you can see that it's oriented in the perfect way to set up the integral with respect to y. However, what I'm going to do is I'm going to set up the integral with both respect to x and with respect to y, so we can see the difference between the two methods. To set up the integral with respect to x, I have to first rewrite each equation so that it's in the form y as a function of x. So rewriting the first equation, starting with x equals y minus 2 squared over 3. So I rewrite it in the form y as a function of x. Right, so I solve for y, so I multiply by the 3 to the right hand side. Take the square root of both sides. So now the left hand side becomes plus or minus the square root of 3x. The right hand side becomes y minus 2. And then adding 2, we see that y is now two functions. So one function is 2 plus the square root of 3x, and the second function is 2 minus the square root of 3x. So the reason that there's two functions for y is that if I look at this curve here, it's not really a function. You can separate it into two pieces. So if I cut it in the middle, so the top piece is given by the function 2 plus square root of 3x, and the bottom piece is given by 2 minus square root of 3x. So the second equation is already in the form y as a function of x. However, we'll rewrite in the form of x equals a function of y because we'll need that later. So if I solve for x, I get x equals 8 minus y. So now before setting up any integrals, I try to find the 2 points of intersection. So this point here and this point here. To get the y values where they intersect, I set the two x equations equal to each other. So this equation I set equal to this equation. So I get this equation, and now I solve for y. So solving for y, you see we get two y values, so negative 4 and 5. So y equals negative 4 is here, and y equals 5 is here. And let's go ahead and compute the x values of these points also. So if I plug y equals 5 into this equation, so 8 minus 5 is 3, so you get x equals 3. So the x value of this point is 3, so this point is 3 comma 5. And if I plug in y equals negative 4, let's mark this as y. This is also y. So I plug in y equals negative 4 into here, I get x equals 12. So the coordinates of this point is 12 comma negative 4. Now we're ready to set up the integral with respect to x. So if we look at the region, we can subdivide the region here into one integral will represent the region to the left, and the other integral will represent the region to the right. So the region on the left, so the x value goes from 0 to 3, marked by this point here. So we integrate from 0 to 3. So the top curve is the curve here given by 2 plus square root of 3x. And the bottom curve is given by 2 minus square root of 3x. So that's the region to the left. Now we compute the area of the region to the right. So now the x value goes from 3 to 12. So we're going from here to here now. Now the top curve is given by the blue line, which is 8 minus x. And the bottom curve is given by the brown curve on the bottom, which is 2 minus square root of 3x. And so this is the integral with respect to x, so the two pieces. Now we're ready to write down the integral with respect to y. We'll see that it's much easier. So first of all, the region varies between y equals minus 4 and y equals 5. So the integral will go from minus 4 to 5. And then now the first function is going to be given by the curve to the right. So this one here. However, we have to use the form where it's in terms of y, because we're integrating with respect to y. So we have to use this form of the equation. So 8 minus y 8 minus y. And then the second function with the curve to the left, so given by the brown one. So it's already in terms of y, so I just write down y minus 2 squared over 3 dy. So this is the integral with respect to y. So if we try to compute the area using each of these two methods, we should see that they're the same. So I actually plug this integral into some software to make the computation quicker. And so we see that this second integral is equal to 40.5. So you can go ahead and try to calculate that, and you'll see that's 40.5. And then now I computed this first one separately, so each of the two pieces. So the first integral to the left we see is equal to 12. And if you compute the second integral here to the right, you'll see that the value is 28.5. And so using with respect to x, if you add these two together, again you get 40.5. So even though one method is easier than the other, they still give you the same answer.